A warm welcome to this session. Okay. A warm welcome to this session. Let's discuss the topic called computer instructions and addressing modes in computer architecture. This is our syllabus, what we are going to discuss today, and those are machine instructions, addressing modes, ALU, data path and control unit, instruction pipelining, memory hierarchy, cache, main memory and secondary storage, and IO interface. What is computer organization and architecture? Do anybody have idea about computer organization and architecture? Or have you wondered how our computers are functioning with hardware digitally? Do anyone? Okay, let's go into deep so that you can understand more effectively. Computer organization is nothing but is a field which explains about internal structure and behavior of digital computers. Its main objective is to make us understand the overall computer hardware structure and all its peripheral devices. And also it tells us how all the units in the system are arranged and interconnected to each other. In a nutshell, when we think of a word called architecture, we think of building a house or building, right? Keeping that same principle in mind, computer architecture involves building a computer and all that goes into a computer system. Computer architecture is a specification describing how hardware and software technologies interact to create a computer platform or a system. Now, let's move on to the next. Here are the subtopics of this session, and let's see one by one. First subtopic is John von Neumann architecture. The von Neumann architecture, also known as the Princeton architecture, is a computer architecture published in 1945 by the mathematician and physicist John von Neumann. His computer architecture design consists of a control unit architecture. All those involves arithmetic and logical unit, memory unit, registers, and inputs or outputs. One human architecture is based on the computer concept where instruction data and program data are stored in the same memory. The key advantage of the von Neumann architecture is flexibility. Because instructions, which is a code and data, can occupy the same bucket of memory. This means that you don't have to commit ahead of time as to how you want to split the limited memory between instruction space and data space. The design is still used in computers produced today. It's what mesmerizing even now. Here is the basic structure of a computer. We all have seen this, we all know this basic structure widely uh, since since we started learning computers. CPU, input devices and output devices are the three main computers that make up the basic structure of a computer system. CPU, which is a central processing unit, can also be separated into two parts. One is the control unit and other is the arithmetic logic unit, which is under the control unit. The basic structure of a computer describes a simple concept. First, the data is entered into the central processing unit using input devices such as keyboard, mouse, joystick, scanner, secondary storage devices, and so on. And when the central processing unit receives the data from the input device, it has a pre-programmed set of instructions to follow. And result of instruction execution is the output device. So that's all about the basic structure. Let's move on to the next slide. Let's see the basic computer structure one by one. CPU. CPU is known as the central processing unit. It is the most critical component of the computer system. It is the computer's brain and it controls practically every unit in the system. Many components make up the central processing unit, including arithmetic and logical units, control units, memory units, and variety of registers. It is sometimes referred to as the microprocessor or processor. Now, registers. Registers are a type of computer memory used to quickly adapt, store, and transfer data and instructions that are being used immediately by the CPU. They are high-speed memory storing units. It is an element of the computer processor. It can carry any type of information, including a bit sequence or a single data. A register should be 32 bits in length for a 32-bit instruction computer. There are five main registers. We all know there are five main registers called memory address register, which holds the memory location of data that needs to be accessed. Second main register is a memory data register. This one holds data that is being transferred to or from the memory. And third one is accumulator, where intermediate arithmetic and logic results are stored. And fourth one is program counter. It contains the address of the next instructions to be executed. Fifth one is current instruction register, contains the current instruction during processing. Understand? Now next, arithmetic and logic unit. Arithmetic logic unit is a digital circuit used to perform arithmetic and logical operations. A modern CPU has a powerful ALU and it is complex in design. Now let's see control unit. The control unit controls the operation of the computer's ALU, memory, and input or output devices, telling them how to respond to the program instructions that has just read and interpreted from the memory unit. The control unit also provides the timing and control signals required by other computer components also. The functions that a control unit performs are dependent on the type of CPU, because the architecture of CPU varies from manufacturer to the manufacturer. So that's why it depends, it varies from CPU to the CPU. Most computer resources are managed by the control unit, and also it directs the flow of data between the CPU and the other devices. Do you understand the control unit? Any doubts in control unit? Okay, let's move on to the next slide. Okay, buses. Buses are the means by which data is transferred between a computer or between a computer system. It is generally a communication system that transfers data between components inside a computer or between computers. A standard CPU system bus is comprised of a control bus, data bus, and address bus. Basically, three types of buses are comprised in buses. So let's see one by one. Address bus. Address bus carries the address of data between the processor and the memory. Data bus carries data between the processor, the memory unit, and the input or output devices, whereas control bus carries control signals, commands from the CPU in order to control and coordinate all the activities within the computer. Now let's see the memory unit. Memory unit is the amount of data that can be stored in the storage unit. This storage capacity is expressed in terms of bytes. The memory consists of RAM and is splitted into partitions, and this partitions, each partition consists of an address and its contents. Both will be in the binary form basically. This address will uniquely identify every location in the memory. Hence, the memory is fast and also directly accessible by the CPU. Hope you understand this memory unit. Do you have any doubts in this memory unit? No doubts? Okay, let's move on to the next. This is the basic CPU structure illustrating ALU. We can deeply go into this. So accumulator stores the results of calculations made by ALU. Next, program counter, which is on the top of the diagram. You can see between the ALU and IR, keeps track of the memory location of the next instructions to be dealt with. The program computer then passes this next address to memory address register, which is called memory address register. It stores memory locations of instructions that needs to be fetched from memory or stored into memory. Next, memory data register. It stores instructions fetched from memory or any data that is to be transferred to and stored in memory. Current instruction register. It stores the most recently fetched instructions while it is waiting to be coded and executed. Instruction buffer register is not to be executed immediately, is placed in the instruction buffer register. And as we can see, input or output devices is read into main memory from the input devices or secondary storage under the control of CPU input instruction, which is a data or a program, whatever it may be. Output devices are used to output the information from the computer. Now let's see the buses. Buses that is transmitted from one part of a computer to another, connecting all major internal components to the CPU and memory by the means of buses. As we have discussed before, we have three types of buses: data bus, address bus, and control bus, which is next to the memory. In the diagram we can see. So hope you understand this diagram. Let's move to the next. Here is a basic computer instructions. Basic computer instructions are a set of machine language instructions that a particular processor understands and executes. A computer performs tasks on the basis of the instruction provided. The basic computer has 16-bit instruction which can be denote either register reference or memory reference or input or output instructions. Hence, we have here 16-bit instruction register starting from 0 to 15. So we will be counting it as a 16-bit register. Now instruction formats. This is the third subtopic which is called instruction formats. An instruction format defines layout of bits of an instruction basically. A computer performs a task based on the instruction provided, as we know already. An instruction comprises of groups called fields. These fields include the operation code field, which we will call in short opcode, which specifies the operation to be performed. And the second one is the address field, which contains the location of the operand, that is register or memory location. Here in this diagram, in the 15th block, L represents the mode field, which specifies how the operand will be located. So these fields contain different information. As for computers, everything is in, as we know already, computers are everything is in zeros and ones, which is a binary language. They usually used to communicate in a binary language. So each field has different significance based on which a CPU decides what to perform. So an instruction is of various length depending upon the number of addresses it contains. Generally, CPU organizations are of three main types. On the basis of number of address fields, we have categorized into three organizations. So let's see one by one. Single accumulator organization, general register organization, stack organization. So let's go into the deep. In first organization, operation is done involving a special register called accumulator. In second, on multiple registers are used for computation purpose. In third organization, which is a stack organization, that works on stack basis operation, due to which it does not contain any address field. On the basis of number of address, instructions are classified. So note that we will use x is equals to a plus b star into c plus d expression to showcase the procedure. So let's see the each of them which are classified further. So here zero address instructions. This is based on the stack. So here we are having A and B stacks. So we are going to push those to the A into B memory. see this. An example, a stack-based computer do not use address field in instruction. To evaluate an expression first, it is converted to reverse Polish notation, that is postfix notation. So hence we are having let's take an expression x is equals to a plus b into c plus d. Now we will be converted this expression into postfixed, which is x is equals to ab plus cd plus star. Now m of x is any memory location. Now let's take m of x is an memory location. Now let's from the postfixed expression, now push the a so that top of the stack will be a. Now next push the b. Now top of the stack will be b. Assume that you are stacking all the elements one by one, which are alphabets. So assume and see one by one expression. So after pushing b, now add both the elements so that top of the stack will be a plus b. Now push c. Now top of the stack will be c. Now push d. Now top of the stack will be d element. Now add both the pushes. Now top of the element will be c plus d. Now multiply them. Now multiply all the stack. So now top of the stack will be c plus d into a plus b. Now let's finally now pop the element x such that m of x is equals to top. M of x already we know that it is a memory location. There all this stack one by one will be residing or stored. In this particular example, you have to assume each stack is being inserted or moved or pushed, so that only you can easily understand this example by yourself. Second one address instructions. This use a implied accumulator register for data manipulation. One operand is in accumulator and other is in register or memory location. Implied means that the CPU already know that one operand is in accumulator, so there is no need to specify it. So opcode indicates the type of operation to be performed. Mainly two types of operations are performed here in single accumulator based CPU organization. Data transfer operation. In this type of operation, the data is transferred from source to a destination. For example, let's take load. We are loading x and they are and storing that x in the y. Here load is memory read operation, that is data is transferred from memory to accumulator, and store is memory write operation, that is data is transferred from accumulator to memory. Let's see the second operation, ALU operation. In this type of operation, arithmetic operations are performed on the data. For example, let's multiply the x. So where x is the address of the operand, the multiplication instruction in this example performs the operation. So here AC is the accumulator and M of x is the memory word located at location x. So we can see here accumulator is multiplied, is stored, it will be stored at last, will be stored in the memory location of x only. So let's see this example. So we are having an expression called x is equals to a plus b into c plus d. AC is accumulator and M of t is a temporary location and M of as any memory location we are storing. So load A. Now first load A, that is accumulated is getting initialized by the memory location of the variable A. So accumulator is equals to M of A. Now add B. So accumulator is getting initialized by the product of accumulated previous content against the variable B. Now A and B is residing in the accumulator. So let us put it in the temporary register called T. So accumulator will be M of T. Store T. Load next load C. So accumulated is getting initialized with the memory content against the variable C. Now we are going to add D to the accumulator such that accumulator is equals to accumulator plus M of D. Next we are going to multiply T to the accumulator such that accumulator is equals to accumulator into M of T. Finally, we will store in a memory location called X. So, M of X is equals to accumulator. To address instructions. This is common in commercial computers. Here, to address can be specified in the instruction. Unlike earlier, in one address instruction, the result was stored in accumulator. Here, the result can be stored at various locations, which is a different locations rather than just an accumulator, but require more number of bits to represent address so that it will be easy. As we have here expression, let's take an expression x is equals to a plus b into c plus d. Here R1 and R2 are the registers. M is an any memory location. Now move R1 register comma A such that R1 will be M of A. We are moving a register A into the memory location. Now we are going to add register 1 to the B. Now R1 will be R1 plus M of B because B is stored in the location. Now next move R2 comma C. Now R2 will be C. Now let's add R2 D to the R2. Then R2 will be R2 plus D. Next multiply R1 and R2. Then R1 will be R1 into R2. Now last move X comma R1. As we all know, X is a memory location. So M of X is equals to R1. Next, 3 address instructions. This has 3 address field to specify a register or a memory location. Program created are much short in size, but number of bits per instruction increase. These instructions make creation of program much easier, but it does not mean that program will run much faster because now instruction only contain more information, but each micro operation that is changing content of register, loading address in address bus, etc. will be performed in one cycle only. Now let's take the expression x is equals to a plus b into c plus d. Here R1, R2 are the registers and M is any memory location. Now we are going to add R1 comma A and B, A comma B. Now R1 will be M of A plus M of B because we are adding A and B to the R1. R1 location. So now we are adding C, D to R2. Then R2 will be M of C plus M of D. Now now we are going to multiply X comma R1 and R2. We all know that X is an memory location to store the registers. Now M of X will be R1 into R2. In order to relieve from confusion, let's see the in a short. Let's see one by one again. Zero address instruction here uses push, which is a stack. It uses the stack basis. And one address instructions uses the accumulator. And 2 address instructions uses the registers. And 3 also uses the registers. in a nutshell, 0 uses the stack, 1 uses the accumulator, 2 and 3 uses the registers. Hope you understand and hope you clarified regarding this without any confusion. Okay. If you have any doubts, let me know. I'll be glad to clarify you. Do you have any doubts? Any doubts? So no doubts?
No, it's clear only.
Hope you have enjoyed this session today and thank you all. We'll meet in the next class.